Welcome to the Walton Pi. Today we're going to be talking about exponential growth and decay. So in some situations, the rate of change is just a scalar multiple of the current value of the function. So for example, maybe you have a situation where the rate that something changes depends on how much you have. So for example, in the bank, the rate that your interest grows depends exactly on how much money you have in the bank. So the more money you have, the more money you will earn. So that's the sort of idea that we're having here. The rate of change is a scalar multiple of the value of the function. So for example, the element copernicium is a very unstable element. Every second, 2.3% or so is going to decay. So that means that if y represents the amount of copernicium that we have, then the rate we are losing copernicium, so y prime of t, is just negative 0.023 times y of t. It's 2.3% of whatever we have, and it's negative because we are losing it. So these sorts of growth and decay problems are always going to be of the form y prime equals a constant times y. We just need to figure out what functions have a derivative equal to some constant times itself. This is a very simple form of a differential equation, which is a common class that you can take, especially if you're going into engineering or something. So if you're interested in that, look into differential equations. So we just have to figure out a function whose derivative is equal to a constant times itself. E to the x, its derivative is equal to itself. So it shouldn't be too surprising that solutions to y prime equals k times y are just going to be a constant times e to the kx. So if we go back to our example with copernicium, every second 2.3% of the copernicium we have will decay into another element. So if we are trying to find a function that describes how much copernicium we have after t seconds, if we started with 1,000 nanograms at t equals 0, we would be able to use the form c equals e to the, or c times e to the kt to help us figure this out. Now, having 1,000 nanograms of copernicium is very unlikely because it is so unstable, but let's just run with it anyway. So if we are losing 2.3% of what we have each second, we know that that means that y prime is equal to negative 0.023y. So using that, we are able to then plug that into the form. We know y is going to be equal to a constant times e to the negative 0.023 times t. If we know that at time t equals 0, there were 1,000 nanograms, we're able to use that to solve for the constant c out front. So we know that 1,000 is equal to y of 0. Y of 0 is just that constant c times e to the negative 0.023 times 0. Well, e to the 0 is just a 1, so this is equal to c. So that means in this case, our constant is 1,000. So we know that y is equal to 1,000 e to the negative 0.023t. Some other things that come up when we are dealing with exponential growth and decay problems are what's called half-lives. So if we are discussing exponential decay, a half-life is the time it takes for exactly 50% of the material to decay or disappear. So if we know the half-life, we could use that to find the equation describing the decay as well. If we're discussing exponential growth, the analog to half-lives is called the doubling time, which is how long it takes for something to double. So if we are dealing with a situation like interest at a bank, if you've put $1,000 in, you might be interested, what's the doubling time at my current rate of interest? You would be able to solve for how long would it take for your $1,000 to become $2,000 using your rate of interest. Let's go through an example of figuring out the half-life of a function. So if we go back to our example with copernicium, we know that our function is y equals 1,000 e to the negative 0.023t. If we are then trying to figure out what's the half-life of copernicium, we're going to need to solve the t. We need to solve for t, where y of t is equal to 0.5, or 1/2 of our starting amount, so 1/2 y of 0. So 1/2 of y of 0, that's 500, because we started with 1,000 nanograms, so 500 is half of it. We are solving for when is 10,000 e to the negative 0.023t equal to 500. So we can divide everything by 1,000, and we get e to the negative 0.023 t is equal to 1/2. If we take the natural log of both sides, we get negative 0.023 t is equal to the natural log of 1/2. If we multiply both sides by negative 1, that's going to make so negative natural log of 1/2 is natural log of 2 using logarithm rules. And then we can divide everything by 0.023. And so we get t is natural log of 2 divided by 0.023, which is approximately 30 seconds. So that tells us that the half-life of copernicium is 30 seconds. Depending on the different situations, you can be able to solve for different half-lives and stuff. If you would like to see other videos where I'm going to go through in more detail how to go about the process if you start with a half-life or finding the doubling time for different problems, check out my next video. I hope this video was helpful. I hope that you're able to understand this a little bit better. Please check out some of my other videos, and if you haven't already, please like and subscribe so that I can continue to make these videos. Have a great day, and good luck with the rest of your math.